Ridge regression. First step, standardize the dependent and independent variable by the subtracting their means and dividing by their standard deviation, and calculation based on the standardized variable. In the ridge regression, calculation is based on the standardized variable. When the final regression coefficient displayed, they are converted into original form. However, ridge trace in the standardized scale OLSC is blue of regression coefficient. If possible, find the biased estimator of regression coefficient, say beta cap underscore, that has smaller variance than the unbiased OLSC. Mean square error of beta cap equals to beta cap underscore MSC beta cap underscore equals to expectation beta cap underscore minus beta underscore का whole square, that is MSC beta cap underscore equals to variance of beta cap underscore plus bias in beta cap whole square, where MSC is smaller than the variance of beta cap by introducing a small bias in beta cap. It is approach of ridge regression, in which ridge regression estimator is obtained by solving the normal equation of least square estimator. Normal equations of least square estimations. Normal equations modified as x dash x plus delta I out of bracket beta cap r underscore equals to x dash y underscore beta cap r and underscore equals to x dash x plus del I का inverse x dash y underscore, where beta cap r underscore is regression estimator of beta. Del is biasing parameter. Here OLSC is inappropriate to use, since OLSC have high variance when multicollinearity is present. So bias in ridge regression estimator, bias of beta cap r underscore equals to expectation beta cap r underscore minus b underscore beta underscore. So expectation in bracket x dash x plus delta I का inverse into x dash y underscore minus beta underscore, which is equals to x dash x plus delta I का inverse into x dash x beta minus beta underscore, since expectation y underscore equals to x beta underscore. So bias in beta cap r underscore equals to minus del x dash x plus delta I का inverse out of bracket beta underscore. Beta cap r underscore is biased estimator of beta underscore. Covariance of beta cap r underscore. Covariance beta cap r underscore equals to expectation beta cap r underscore minus expectation beta cap r underscore into beta cap r underscore minus expectation beta cap r underscore का whole dash. So beta cap r minus expectation beta cap r underscore equals to x dash x plus del I का inverse x dash y underscore minus x dash x plus del I का inverse x dash x beta underscore, which is equals to x dash x plus del I का inverse x dash u underscore. Thus covariance beta cap r underscore equals to x dash x plus del I inverse x dash expectation u dash u underscore u dash underscore into x dash x plus del I का inverse, that is variance of beta cap and r underscore equals to sigma square x dash x plus delta I का inverse into x dash x plus delta I का inverse. MSC beta cap r equals to variance of beta cap r underscore plus bias in beta cap r underscore का square, that is trace of sigma square x dash x plus delta I का inverse into x dash x plus delta I का inverse plus minus del x dash x plus delta I का inverse beta underscore का whole square. Means MSC beta cap and r underscore equal to sigma square j takes value from 1 to k lambda j by lambda j plus del का whole square plus del square beta dash underscore in bracket x dash x plus del I का whole inverse beta underscore, where lambda 1 lambda 2 and so on lambda k are eigenvalues of x dash x. As del increases, the bias in beta cap r underscore also increases, but its variance beta cap r underscore is decreases. Since there exists a value of delta such that MSE of beta cap r underscore is less than variance of small b underscore OLSC of beta underscore. Ridge trace. Ridge trace, if multicollinearity present and severe, then it is used. No, ridge trace, if the multicollinearity is present and severe, then instability of regression coefficient is reflected in the ridge trace. The objective of ridge trace is to inspect and the reasonable small value of del at which beta cap r underscore is stable, and for such del MSC beta cap r underscore is less than variance of OLSC. A graph in such a way where del is on the x-axis and beta cap k underscore on the y-axis. Beta 1 underscore cap underscore beta 2 and cap underscore and so on, beta 5 cap underscore beta 6 cap underscore. Estimates. For a small value of del, the change rapidly for the small value of del, beta changes rapidly, and as del increases, it stabilize gradually. So the value of del, all estimates stabilize desired value of del. The value of del at all the estimates stabilize are the desired value of del. x1, x2 and x3 are totally independent in the graph, and beta 1 cap underscore beta 2 cap underscore beta 3 cap underscore independent, beta 4 cap underscore is a straight line, while beta 5 underscore is less than the beta cap 6 underscore at the high value of del, but at the low value of del beta 5 is above the beta 6. So intersection of beta 5 and beta 6. Simultaneous equations. In a real life, variables that are depend on each other are called simultaneous variable. No, in a real life, variables that are depend on each other. In some situation, y is determined by x, that is y is function of x, and in some situation and sum of the x determined by y, that is x is function of y. Thus, there is simultaneous or two-way relationship between x and y. A system describing a joint system of a joint dependence of variables, system of simultaneous equations or simultaneous equation model. Endogenous variables regarded as stochastic variables and their values are determined within the model. Endogenous variables are regarded as stochastic variables and their values are determined within the model. The variance which affect the system and affected by it. The variable which affect the system and affected by it. The variable means endogenous variable act as both dependent and independent variable. And endogenous variable in conventional notation, endogenous variable denoted by y, and it is regarded as stochastic variables. Their values are determined within the model. Conventional notations endogenous variable denoted by y. It is act as both dependent and independent variable. These are variables which affect a system and affected by it. Exogenous or predetermined variable. It is non-stochastic variable and it is given in the model. Their values are given within the model. The exogenous variable or predetermined variable which affect the system but not affected by it. It affects the system but not affected by it. Purely independent variable. Purpose of explaining endogenous. These are purely independent variable and the purpose of exogenous variable or predetermined variable to explain endogenous variable. The conventional notations exogenous variable is represented as Keynesian model of income determination or theory of consumption. Consumption function Ct equals to beta naught plus beta 1 Yt plus Ut, where Ct is consumption expenditure, Ut is stochastic disturbance, and income identity. We have to consider consumption function and income identity. Income identity Yt equals to Ct plus It, where It is investment, or in bracket delta T which is savings, St which is savings, and Yt is income at time t. First equation 1 consumption function and income identity. Equation 2 beta 1 marginal propensity to consumer, that is rate of change in consumption for a unit change in equation 1. Rate of change in the consumption for a unit change in equation 1. Unit 1 stochastic consumption function. Equation 1 stochastic consumption function. Equation 2 national income identity. Reduced form of model Ct equals to beta naught plus beta 1 Yt plus Ut, this is equation 1, and Yt equals to Ct plus It, this is equation 2. So putting Yt value in the equation 1 from equation 2, 1 minus beta 1 Ct equals to beta naught plus beta 1 It plus Ut. So Ct equals to beta naught by 1 minus beta 1 plus beta 1 by 1 minus beta 1 into It plus Vt, where Vt is Ut by 1 minus beta 1, which is reduced form of disturbance term. This is the equation 3. And now putting this equation 3 is the Ct value in equation 2, we get Yt equals to beta naught by 1 minus beta 1 plus 1 by 1 minus beta 1 it plus vt. This is equation 4. Equation 3 and equation 4 are reduced form of model. Estimation of all parameters necessary condition. Number of equations equal to number of endogenous variable. Endogenous variable. Number of equations. Problem associated with simultaneous equation or the, the simultaneous equation bias and inconsistency of Euler's estimators or assumption of Euler's estimators are violated in simultaneous equation model. This implies in simultaneous equation model explanatory variable x and disturbance term u not independent, that is expectation x into u not equals to 0. This implies covariance x comma u not equal to 0. So one of the important assumption of OLS that x and u are uncorrelated is violated. As a consequence, OLS is biased and inconsistent. Consider a simple simultaneous equation model. Y equals to alpha naught plus alpha 1 x plus u, x equals to beta naught plus beta 1 y plus beta 2 z plus v, where u v are disturbance term, x y are endogenous variable, y and z x y z y and z z only z are exogenous variable because x y are already endogenous. Consider, okay, here assumption are expectation u equals to 0, expectation v equals to 0, expectation u square equals to variance of u equals to sigma square u, expectation v square equals to variance of v equals to sigma square v, expectation ui uj equals to 0, I not equals to j, expectation vi vj equals to 0, I not equals to j, and expectation u into v equals to 0. From equation 1 in 2 we have putting value y, that is x equals to beta naught plus alpha naught beta 1 by 1 minus alpha 1 beta 1 plus beta 2 by 1 minus alpha 1 beta 1 z plus beta 1 u plus v by 1 minus alpha 1 beta 1. From equation 1 in equation 2 we what we get, this is reduced form. Okay, now we can prove that covariance x u equals to expectation x into u equals not equals to 0. So covariance x comma u equals to beta 1 by 1 minus alpha 1 beta 1 into sigma square u. Thus covariance x comma u equals to expectation x into u not equals to 0. Hence assumption of classical linear regression model violated. Now we have to prove that alpha 1 cap equal is biased. An inconsistent estimator of alpha 1 from equation 1 y bar equals to alpha naught plus alpha 1 x bar plus u bar which is 0, since expectation u equals to u bar equals to 0, y minus y bar equals to alpha 1 x minus x bar plus u, small y equals to alpha 1 small x plus u. It is deviation form of given model. Apply OLS to this model, that is multiply it with x and taking summation. We get summation xy equals to alpha summation x square plus summation xu. divided by summation x square summation xy by summation x square equals to alpha 1 plus summation xu by summation x square. So alpha 1 cap is OLS of alpha 1. Expectation alpha 1 cap equals to alpha 1 plus expectation summation expectation u x by summation x square. Since expectation xu not equals to 0, thus alpha cap 1 cap is biased estimator of alpha 1. An estimator said to be inconsistent if its probability limit equals to its population value. If alpha cap consistent estimator of alpha, then alpha 1 cap in probability tend to alpha as n tend to infinity. Here alpha cap OLS equals to summation xy by summation x square. It is same as the other model y equals to alpha plus beta x plus u. So here beta equals to alpha 1. Quite same. So probability limit alpha 1 cap equals to probability limit alpha 1 plus probability limit summation ux by summation x square. Probability limit alpha 1 cap equals to alpha 1 plus probability limit summation ux by n summation x square by n. Probability limit alpha 1 cap equals to alpha 1 plus probability limit summation ux by n probability limit summation x square by n, where 1 by n summation ux is the sample covariance between x and u. 1 by n summation x square is sample variance of x. Since probability limit summation u x by n equals to covariance x comma u, which is beta 1 sigma square 1 minus alpha 1 beta 1, probability limit x square summation x square by n equals to sigma square x equals to variance of x. Thus probability limit alpha 1 cap equals to alpha 1 plus beta 1 by 1 minus alpha 1 beta 1 into sigma square u by sigma square x. Hence probability limit alpha 1 cap not equals to alpha 1. Therefore alpha 1 cap not a consistent estimator of alpha 1. Identification problem. The problem of model formulation rather than of model estimation. A model is said to be identified only when it is in unique statistical form to enable us to obtain the unique estimates of its parameters from its sample data. And a model is said to be complete if it is contains at least as many independent equations as endogenous variables. That is, number of equations is greater equals to number of endogenous variables. For identification of the entire model, it is necessary for model to be complete and each equation to be identified. Situation of identification: under identification, exact identification, over identification. Under identification, the estimation of parameters is not possible at all. No enough estimates are available for the structural parameters. Means number of equations is less than number of endogenous variable. And exact identification, when number of equation equals to number of endogenous variable, the estimation of parameters is possible in this case. The OLSEs are reduced from coefficient leads to unique estimates of the structural coefficient in the exact identification. And for over identification, the estimation of parameter is possible in this case. The LSC are reduced from coefficient leads to multiple estimates of structural coefficients, which is this is in this number of equations is greater than number of endogenous variable.